Students, welcome back to another day in science class. And today, I'd like to wish you a saying, may the force be with you. Because this week we are, as you know, talking about forces. So let's get to our notes at this time. Open your books and let's check out some information about our topic of the week, forces. So let's take a moment first and see if you can answer this following question. Wrong question. What is force? Or what is a force? Take a moment and discuss. Okay. From a scientific point of view, a force can be defined as a push or a pull on an object, any object. A push or a pull on an object. Maybe some of you have had to move things from one place to another. In order to do so, you have to apply a force, either a push or a pull on an object. How many of you have ever moved something around? Can you give any examples of things that you have moved? And how did you move it? How do you think a force was involved? Very good. All right. So now here's another piece of info about forces before we dive in a little bit more to them. Forces can either enhance or cancel one another. Well, you'll notice I put those little plus sign and negative sign above these words. Forces can enhance one another, be added together, or they can cancel one another or subtract from one another. So what in the world does that actually mean? Well, here's a good example, I think. Think of a typical tug of war. How many of you have ever been in a tug of war? And if you were to have a tug of war in the classroom right now, who would you want on your side to help you? Okay. You would want those individuals who would be able to enhance or add to your force as much as possible, as opposed to folks who would not be able to enhance or add to your force. Now, I want to demonstrate a simple tug of war with you. In case you don't have experience with what tug of war is, I just so happen to have a volunteer here with me right now in the studio to assist me in demonstrating a tug of war. Check it out. All right. They are, by the way, his name is Slim. He's at the other end of this rope that I am holding right now. And I want you folks watching to say 1, 2, 3, go. And as soon as you say go, I am going to apply a force myself. And we'll see if Slim is able to apply a force in the opposite direction here. But I'm going to apply a force in this direction. And let's see who wins our little tug of war competition. Are you ready? So give me a 1, 2, 3, go. I think I'm winning. Here we go. Come on. I think I got it. Yeah. Come on. Oh, yeah. I got him. Woohoo! Yeah, baby. I think I won that tug of war. Oh no, he's following me around. No, wait, Slim, no. Sorry about that. I think I really just put my foot in my mouth. All right, let me give that back to Slim. Here you go, buddy. All right, now hopefully you could see from that demonstration who was exerting a greater force. Was it Slim or was it me? Yeah, it was me. Probably for obvious reasons, but I won that tug of war. Yes, I'm so proud of myself. I defeated a plastic skeleton with no muscles at all. And yet, it looked like I was struggling, didn't it? Right. So, now here's the deal with forces. I wish I could have a tug of war with you guys right now in the classroom. That would be so much fun. But we're not going to do that right now. So here's the deal forces can either enhance one another or cancel one another. I just want to demonstrate both of those right now. Let's say we have an object that is being pushed by different individuals in opposite directions. This one is pushing it this way, this one is pushing it this way. They're both pushing in opposite directions with equal force. What do you think is going to happen to that object? What do you think? Will it move or will it stay put? You probably said stay put, right? It's not going to move. Why? Because these two forces are canceling one another. They're basically in opposite directions. You're subtracting the net forces, and it results in no movement whatsoever. The object stays put. It stays stationary. But look at the bottom example here. In the bottom example, we have one person pushing this object and another person pulling this object. And they're both applying a force, a push or a pull, in the same direction. Well, what do you think is going to happen to this object? Do you think it's going to stay put or do you think it's going to move? Yeah, it's going to move, especially since it's on wheels here, but it's going to move in the direction that they are applying the force. Their two forces, the pushing force and the pulling force, are being added together. And so there are two net forces pulling in that direction, and so they are helping each other. That's a good thing when you can help each other. So sometimes when you need to accomplish a task, it's good to ask for a helper, somebody to give you a hand. And if you are working together in the same direction, then it will be a help. Now, if you're both like the folks in the upper example, pushing in opposite directions, you're not going to get anywhere very quickly. Now, what we just demonstrated here, what are called unbalanced forces. You see, in the first case, the forces were totally canceling each other out, and so there was no movement whatsoever. The object stayed still. But in the second example, there were unbalanced forces. There was a greater force in one direction than there was in another direction, and that caused movement. Just like in the example of the tug of war earlier. I was applying a greater force than Slim was applying. And since Slim wasn't applying really any force whatsoever, my force was greater. It was an unbalanced force. And as a result, he moved in my direction. So unbalanced forces result in movement or motion, which is what last week's topic was all about. Now, have any of you ever played on a seesaw or a teeter-totter? People call them both things. Anyone ever play on a seesaw? Raise your hand if you've ever been on a seesaw. Have any of you ever been in a situation like this where perhaps you were younger, thinking back to your younger days, and you wanted to seesaw with maybe your mom or dad, aunt or uncle, or somebody that's older and bigger than you, and you got on the seesaw and then they got on, and they tortured you because you couldn't get off. Can you imagine? I can imagine. I used to do that to my daughters all the time when they were younger. I'd like sit down and they'd be up in the air and like, it's time to let me down, Dad. But of course, I wouldn't torture them that long. It was just kind of fun to do. But you can see what happens if there is an unbalanced force. It results in movement. This dude up top, he has moved off the ground. Now, picture, if you would, the teeter-totter being like this, the seesaw being flat, and having the little guy on the bottom end, and then having the other dude jump on his end. How much movement do you think there'd be then? Whew, that would be a cool experiment, I think. If you've ever played the game Mousetrap, you know what I'm talking about, when the guy dives into the little bucket and boing, throws him off. Actually, it's what throws him into the bucket. Raise your hand. Have you ever played Mousetrap? Oh boy. If you've never played Mousetrap, it's a great game to play. Great physics. Maybe I'll have to get it out in a couple weeks, and we could demonstrate some things with Mousetrap. It's a great game. All right, let's move on. Now, there is another force. There's another force among us, and that other force is acting against us all the time. It's a force in the opposite direction of motion, and that force is called friction. Friction is always moving in the opposite direction of motion, and it is a force that we really want to overcome most of the time if we're talking about machines helping us move something from one place to another, like a bicycle or roller skates or a car. We want to make sure that they're well lubricated in various places to minimize friction. Because if there's too much friction, it can build up heat energy and all sorts of other things. In fact, we could demonstrate this right now. At your seats right now, what I'd like you to do is demonstrate friction with your hands. Take your hands out in front of you, and when I count to 3, I want you to clap 10 times really hard, and then rub your hands together while I count to 10 and see what you experience. Are you ready? 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Rub, 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 rub. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now touch your face. What do you feel? What do you feel? Do you feel the heat? Can you feel the heat today? Yes, the heat is from the friction, the frictional force between your hands when you were rubbing them together. You were rubbing in one direction. The friction was a force in the opposite direction. So you keep on rubbing back and forth. That friction builds up heat energy, and boy, woo-wee, my hands are still warm from that. But friction is a force that acts in the opposite direction of a moving object. Now, I know many of you have bicycles. Maybe you've been out riding bikes lately in the afternoons. Have you ever ridden a bike really fast and you get off the bike and you feel the tire? The tire is probably going to be hot from the friction. Or how many of you have ever gone roller skating? If you've ever gone roller skating or rollerblading, have you ever gone around and around and around and then felt the wheels? The wheels probably got hot. That's a result of the friction working in the opposite direction of your movement. And again, there are things we can do to minimize friction if we want. I mean, there might be sometimes we want to increase friction. Like here's an example, the classroom doors. If you want to keep a classroom door open and so that you don't have to touch the handle, what do we put by the classroom door? Those little wedge things, right? And if you've noticed those little wedge-shaped blocks, they have a rubber pad on one side. Why? to increase the friction to prevent something from moving. So sometimes friction can be a good thing, sometimes it can be a bad thing. It certainly depends upon the context, but both good or bad, it always is the same force. It is a force acting in the opposite direction of a moving object. Okay, I think we got friction pretty well understood here. Let's move on to Newton's, and that's Sir Isaac Newton's 3 laws of motion. Let's summarize these 3 laws of motion now. Let's begin with number 1. Number 1, here's a little cartoon about a superhero called Inertia Man. And let's see if I can read this. Inertia Man, come quickly. If we don't stop the evil brains robot army from triggering the doomsday machine, Mega City will be destroyed. And Inertia Man says, I'll be right there. 20 minutes later, boom! Mega City is destroyed. Why? Because they called on Inertia Man. And who is Inertia Man? He's just a fictional character, but inertia is a word, and inertia is the Latin word for lazy. How many of you have inertia? Well, you all have inertia. Inertia is a property of matter, if you think back a few weeks ago, and it is a property that we all possess. Now, it doesn't mean that we're all lazy in the context of a work ethic, but it does mean we are all lazy in the context of physics. You see, inertia can be described as an object that is either at rest or in motion, wanting to stay that way until acted upon by a force. You may recall a couple weeks ago we talked about being in a car, zoom, 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 and how important it is to have a seatbelt on. And if you don't have a seatbelt on and the car stops abruptly, you will have nothing to hold you into that car because you have inertia. An object at rest or an object in motion will remain that way until acted upon by a force. If I were to place this roller skate on my hand here, on my arm, how long do you think it will take for the roller skate to roll all the way off my arm and onto the floor? How long do you think it will take? Well, let's watch it. Oops. What just happened? Well, a force acted upon it to knock it over. But if I just hold it completely still and don't move at all, and I am exhibiting a laziness, a position at rest, how long will it take? It'll take an eternity because it has to be acted on by another force in order for it to move. An object at rest will stay at rest. An object in motion will stay in motion unless it's acted upon by another force. So that is Newton's first law of motion, which can be summarized in one word, and that one word is inertia. In fact, in your notes, why don't you either circle or put a box around the number 1 and the word inertia? Great way to study for your quiz. All right, number 2. Number 2 can be summarized with an equation, a formula. So as you're writing this down in your book, again, next to number 2, you're going to write F equals M. And does anyone know what's happening between the M and the A? Multiplied. M and A are being multiplied here. This is the summary form of Newton's second law of motion. Now, here's a picture of a dude trying to do something. What is he doing? Yes, he's pushing a car. Now, is he able to push this car very fast? I don't think so. Why? Why? Because the car is really heavy. And it looks like he's going up a little hill here too. The car has a lot of mass to it. Force, mass, and acceleration are all connected in Newton's second law of motion. This formula states that force, and that's really not a negative sign in front of force. You don't have to write that. It's just like a little mark saying this is one important piece of information. But force is equal to mass times acceleration. So force, mass, acceleration are all connected. And let me try and illustrate it with a saying here. It probably makes sense with these words. The harder you push, the faster you go. Now think about that for a moment. Let's say if I were on my wheelie chair here and I were to ask one of you to come here and push me around the room or push me around the hallway. How cool would that be, right? I'd love to do that. And you could push me lightly to make me go slow, or you could push me really hard to make me go super fast. What would you choose, by the way? Would you want to push with a gentle force or with a really high force? Yeah, I figured as much. You'd want to push with a really high force to make me go really, really fast. And then you'd probably want to stop me short, right? Knowing that I don't have a seatbelt on. And if you stopped me short, what would happen to my body? Yeah, I'd go flying off of the chair and onto my face because I would possess what property of matter, everybody? Inertia is correct. Very good. So Newton's second law of motion, the harder you push, a measure of force, the faster you go, a measure of acceleration. Now, remember last week when we talked about the mouse and the elephant? Well, think about the mouse and the elephant for a moment. Let's say you had one chair with a mouse, one chair with an elephant, and you pushed both of them with the same force. Who do you think is going to accelerate faster, the mouse or the elephant? Pause me now to discuss this. All right, you probably said, well, yeah, the mouse, to be sure. Why? Because it has a smaller mass. Because mass is going to affect the acceleration based on the force that you push. So you use the same force with two different masses, it's going to result in different accelerations. Here's another example. This phrase here, have you ever heard of this one? The bigger they are, the harder they fall. Think about that for a moment. Do any of you heat your homes with wood? Have any of you ever chopped down a tree? Anyone ever see a tree being chopped down? Well, let me tell you something. I've cut a few trees down in my day, and I can attest to this, the truth of this statement. The bigger they are, the harder they fall. You take an itty-bitty little sapling tree and you cut it down, bloop, it goes down with a great deal of ease. You get a big tree, however, and you chop that down, when that sucker hits the ground, and you better not be in the way, that's for sure, you can feel the entire ground vibrate for real. Why? Because the more massive something is, it's going to result in a different force if it falls down with a certain acceleration. I mean, a tiny tree, not much mass. When it falls with the acceleration of gravity, it's going to produce a little force. A big tree, however, when it falls down with the acceleration of gravity, same acceleration of gravity, it's going to fall down with a much bigger force. And like I said, if you've ever been around a tree that is felled in the woods and it's a big one, you can feel that. Or how about just, playing out in your front yard and a motorcycle goes by and a tractor trailer goes by. Sometimes when a big tractor trailer goes by, my house anyway, you can feel the ground rumbling even in your house, much less your front yard. Why? Much bigger mass. It's going to affect the force that much more. All right, that brings us to the third law of motion. Third law of motion is probably Newton's most famous law of motion, action-reaction. Again, as you're writing this in your notes, circle or put a box around action, reaction, so that when you are studying, it kind of pops out at you. Action, reaction. It's what enables us to send rocket ships out into space. To elaborate, we can say that for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Now, I'm going to stop this lesson after we all have this written down because I want to show you some videos about these Newton's 3 laws of motion. So once we have this written down, action, reaction, I think the best way to demonstrate Newton's laws of motions are to show you. So I, for today, am going to say bye-bye for now and check out the following videos.